Good morning, everybody. I think we're live here. Welcome to the third in our MSAM series, where we're looking at Canadian problems and how 3D printing is helping to solve them. So we've actually got two stories for the price of one today. We've got Dan from Cycling Canada and Ben from Gibli Tech with us. We're just going to wait for another minute or so while people come in. So I think in the Q&A, if you just click on the Q&A top right, I think Megan, who is playing our brilliant support role, she should have put in there 3 statements, whether you're from, let me just check that we have got that right, whether you're from industry, whether you're a researcher, or none of the above. And if you could just like the appropriate comment, that would be great. And you can type your questions into the Q&A, and we will try to answer them towards the end of the presentation. The only thing I would ask there is, could you please give us a name and maybe an organization, just so that we have some context, and if we're not able to answer it live, we can follow up with you. That would be really helpful. And as always, if you think that you have a story that we should tell, then please do reach out to me or to Professor Bschaden, anybody at MSAM at Waterloo, and we would be delighted to tell your story. A sneak preview, it's not really a preview, but it's a verbal preview. We are going to be doing some deeper dives into the processing, into the need for high-performance aluminiums with materials like scalmalloys, and we're going to be doing that featuring the Barnes Group and one of our lead researchers, Sagar Patel. So that will be coming up in a couple of weeks. So that will be more of a technical deep dive, probably with more equations than we've got today. So as I said, the star of the show today is Team Canada, and representing Team Canada, we're very pleased to have their head mechanic, Dan Peters, who I think on my screen is appearing as Teams Live Guest 1. I don't know if you're on wave to us, Dan, just so, so people can see who's Dan. And we've also got Ben, probably going to not make a good name of your surname, Bschaden. He's the CEO of Gibli Tech. And when I first met Ben at the beginning of this project, he kept me very much in the dark and wouldn't tell me exactly what Gibli Tech were doing, what their device was. All I was told is I had to print a bracket to hold the device so that it could be tested. So I'm going to sort of repay that stealth favor, and we'll keep Ben in stealth mode for a little bit, but we're certainly going to hear more about Gibli Tech, and we are going to find out exactly what the company is all about, what the device does. So we do have Sagar Patel. He'll be joining us, and if we do have some technical questions on the physics of laser melting, we will have people who can answer those questions. I'm expecting that there might be some more questions about cycling and what Gibli Tech are doing than the physics of laser melting, and that's fine. So as I said, if you can, when you do have questions, type them into the Q&A. If you could give us a name, that would be great. So Megan, I'm not sure I can see the distribution of likes and where we've got people from, but it looks like we've got about 30 people in the meeting now. So I think it's probably about time that we got started. I don't know in the Q&A if we could just see, do we have anybody? I was thinking, let's see who's come from the furthest afield. Do we have anybody from California? Anybody from London? Anybody want to beat those kind? That would be London, UK, as opposed to London, Ontario. I can see that we've got 11 people, 12 from research, 7 from industry, and 2 from other. And of course, you could be from all 3. So anyway, Again, welcome to this. I hope you're going to enjoy it. And what we're going to start with is a short show reel. This is just like Netflix, where this is the trailer, and hopefully you're going to want to stay for the rest of it to get the answers to who done it. So, Megan, do you think you could play the show reel for us, please? Great, thanks very much. And as always, I say a big thank you to everybody who contributed to making that video. Everybody at MSAM, Dan's team at the track, Ben, obviously quite difficult to put stuff together under COVID conditions. So thank you very much. And Maria, who is our video editor in the background. So once again, let me please welcome Dan Peters live to our webinar. So Dan, you're head mechanic for Team Canada. I'm a Formula One fan. There are lots of mechanics in Formula One, but what does your job entail as head mechanic? And is there any such thing as a sort of typical day in the life right now?
Thanks, Mark. Yeah, as a Formula One fan as well, there are parallels to be made, of course, and their budgets are far exceeding ours. So I do the job of 30 Formula One mechanics, just on a smaller scale. So as the head mechanic, I'm responsible for working with a lot of our suppliers on products and feedback and development, regardless of what aspect of the bike they might be. I'm responsible for all of the purchasing. If we are not working with a sponsor, I'm responsible for purchasing the items that we actually need for the bikes and for the equipment for the team. Sometimes I have to drive a truck across Europe. I'll work the races. I'll be at the track on a daily basis in the training environment and helping the athletes and putting out fires, maintaining the bikes, basically everything involved with the equipment. The hard goods of the sport is sort of my purview as head mechanic.
And do you actually, when you go off to races, you go to the Olympics, the shipping and assembly, presumably the bikes have to be disassembled and reassembled. Is that something that you have to do as well? Do you have a team of people helping you, or is it more or less just yourself?
No, that's an interesting question, actually. So based on the size of the sport and the budget of the sport, when it comes to actually the logistics of doing a race, we do have a team, a couple people that deal with bookings and hotels and tickets, that sort of thing. But when it actually comes to packing, unpacking, transportation, and the bikes, that is a big part of my job when it comes to races. In a larger scale, let's say you had a European professional road team, or you had a Formula One team, or sailing, you would often get a carnet, an international declaration, and you would have the same list of kit that would get packed up, picked up by a logistics carrier, shipped to your location. You would then just fly with your suitcase, land at the location, assemble everything, do the competition, repack it, again with the carnet, and ship it back home. Mm-hmm. But due to the nature of our sport and the budget and where we're going and when, and the fact that we don't have multiple of everything, most of the riders have one racing bike, we actually need to pack up the equipment the day before we fly, put the equipment on a plane with us, on a commercial plane, which can often be a real hassle, land, drive it to the venue, unpack it, do the race, pack up again, get it all back to the airport, fly home, and unpack. And it's a major challenge. And a carnet makes certain things easier and it makes certain things harder, and an international shipper makes certain things easier and harder. But right now, it's basically just done on commercial flights.
Okay, fascinating. So, let's just, before we are going to talk about the bikes and the bits and the science, but I'd like to focus a little bit more on the people. And I guess in Canada we've got about 40 million people, haven't we? And maybe 20 are going to make it to the Olympics. So the people that you're working with, Dan, they must be truly extraordinary. So can you tell us a little bit about what does it take to be an Olympic cycling athlete, and what really makes them unique? What's it like working with them?
Yeah, they are unique, absolutely. I would say that it takes two solid aspects of character to make it. So one is the genetic predisposition. These people are genetically gifted. They are not the regular weekend warriors. There is something in their DNA that makes them more predisposed to put out more power at a lower heart rate and metabolize oxygen better than most folks. And to measure those things, or to find people with that genetic predisposition, we have a bunch of different ways. We have various lab equipment. We have power meters on bicycles. We have a youth development program in racing across the country to help identify people who are just special, going faster. And that in itself isn't enough. Because it's one thing to be incredibly physically talented, but if you're not tough enough mentally, if you're not resilient and tenacious, and you don't have the drive to go better, go faster, and be better, and do this day in and day out, often in the rain, in the sun, in the wind, and for years at a time, because most of our athletes, at least in the track program, will have a 2 to 8 year career. So to do this day in and day out, it requires somebody special, mentally and physically. So they are unique. They have something else that most of us don't. And in addition to that, it's finding these people. So of 1,000 cyclists that we might see, only one of them is going to be really special, or is really going to have what it takes to be an Olympic medalist or a world champion. And the challenge with that is that cycling in Canada is not the most popular sport. We have hockey, and we have soccer, and we have other sports that either have an easier entry into the sport, they're less expensive to participate, or they're just more popular. We have a culture of hockey. With cycling, half the winter, you can't ride outside, depending on where you are in Canada, of course. But there is an aspect of actual talent identification, getting youth into the sport, finding adults who are exceptional and have the interest in it. So there's a lot of pieces, not only finding the right people, but just finding enough of them, finding that needle in a haystack. And that's what makes it, so special that these, let's say for Tokyo, we're going to have 20 Canadians in cycling representing Canada of those 40 million. And it took everything we had to find those best 20.
Fascinating. Yeah, and as you said, so we've got, not only do you have to fly your own bicycle on a commercial flight, and I think the story, didn't we win when we won our first gold medal? I think the athlete was actually using borrowed wheels or something.
Oh yeah, that's an interesting one. So the way that Sport Canada has worked with government funding, and the way that money has been distributed to the various NSOs, national sport organizations, whether it's athletics, swimming, cycling, you name it. There was a time when there was not as much funding, and there was not a simple system for how that money was divided. So in 2004, we had a woman named Lorianne Munzer, and she was competing in track cycling. And the Canadian national team didn't have much money, if any money, or support for her. And she ended up going to the Athens Games, and we didn't have equipment to help her. And I don't know what we had at that time. This is before my time. I don't know what we had to support her with, but she ended up having to borrow wheels from Australia to compete in the finals. And then she ended up beating an Australian woman in the finals to win the gold medal. So, they kind of kicked themselves in the butt there.
The true Olympic spirit, I guess.
Yeah.
So,
yeah.
So, as you say, Athens was before your time, but I guess Tokyo is probably going to be your third Olympics, at least, Dan. And I guess during that time, you've seen the science behind the sport changing. And can we dive in a little bit about what you've seen happen? I guess maybe was London your first Olympics, and tell us a little bit about the evolution that you've seen.
Sure. Yeah. So I started with Team Canada at the beginning of 2012, and I didn't attend the London Games, but I did get kind of on board, and then I continued on after it. At that time, we had a mechanic in place who he was transitioning out and I was transitioning in. So my first games was Rio, but I was fully on board with what was going on, and post games I learned most of what we had developed and put forward for that game. So I'll share with you now a quick PowerPoint that starts to detail the evolution of our hardware and of our bikes, and where we were and why we were there and where we are now. So you've got three images. On the left, you've got Tara Whitten riding in the London Olympics. In the center, you've got Laura Brown riding in the Rio Olympics. And on the right, we have Annie Foran-Mackey. This is just a snapshot from some testing that we did with our Tokyo bike and position. It's not the final hardware, as you'll see soon, but it is the final position. So there are three things that have always controlled or influenced the positions that we have, the hardware that we have, and why for these bikes and for these positions. This sport that I'm showing you is the team pursuit. It's 4 riders on the track, riding 4 kilometers from a standing start, and in the finals they'll race against another team on the other side of the track. But the real important thing about this discipline or this sport is it's a team event, it's a timed event, and aerodynamics and power output and coordination are really paramount to success. So in the image on your left, London Olympics, Tara Whitten, this was a bike that we got from our sponsor at the time, Look, and the defining piece of a lot of these bikes is the front end, the aero bars, because as we know with aerodynamics, it's frontal area and how streamlined that frontal area is. So the handlebar that Tara is riding here, you can see it's got these red grips down on the bottom that come up and extend into a white extension and arm pad. So we'll refer to the red piece as the base bar and the white piece as the aero bars or the extensions. And back in 2010-11, when we had this produced, we were very much a David and Goliath type team. We actually still are, maybe not to the same scale, but this piece was developed as a carbon wrapped design. So we had some hardware, we had some more generic aero bars, and they were mishmashed and cut up and carbon wrapped to create a single one-piece carbon bar. And at the time, it was pretty groundbreaking for us. We had never done anything like that before. It was incredibly expensive because they were nearly bespoke for each of the riders on the team. And there was also rules that dictated how the rider could ride the bike or what positions they could take on the bike. So if you look very closely, you can see Tara's forearms are basically level. And this was a stipulation of the technical regulations. We had to have flat arms. There was also stipulations around how far forward or back the saddle could be, how far forward or back the handlebars could be. So not only
just like Formula One, there's a rule book and you have to follow it. Yeah,
okay. And it's changing. In Formula One, it changes usually every year. Yeah, and for us, it often changes every quadrennial, every 4 years. So we had these rules, we had to live by them, and our knowledge of aerodynamics was not where it is now. So at this time, this was a great position. The helmets were fast, the bikes were fast, the wheels were fast. We thought we had a pretty good kit, and we ended up finishing third in London. The next iteration, or the central picture of Laura riding here, we made a very significant change, because not only did the rules change, we had more control of the saddle positions, the bar positions. We didn't have this stipulation that the arms had to be flat anymore. We could actually angle the arms. And we learned very, very early on that angled arms having your hands as high as possible and your elbows as low as possible was 100% faster in every situation. It never made sense to have flat arms. So that had to change, and the hardware had to change for it. In addition to that, we were able to access more aerodynamic testing. So we had a system that allowed us to do some aero testing at home at our velodrome, sort of in a simulation of a wind tunnel. But it was tedious, it required a lot of work, and it was very disruptive to training. So we pulled it out when we needed to answer questions, but we couldn't do it all the time. And through this testing and through this learning and the rule changes, we decided that a very, very wide arm position that was also very low and had the hands angled higher than the elbows was going to do a few things. It was going to be faster than the London bike. It was going to give the riders great visibility and great control, because we went from having narrow and tight and low to having basically like a semi-truck steering wheel. You had this big monster truck that you could drive around, and the riders had great control of the bike and great visibility. And we found that if they could ride closer to their teammate in front of them, if they could ride more stable and in a straighter line, they were going to travel less distance on the track to complete the 4K. They were going to get more recovery when they were in positions 2, 3, and 4, because they ride in a line. And they were going to be slightly more aerodynamic because we were able to get them lower and bring these hands up. The challenge here, though...
So this was sort of you're optimizing the system, and the system here is 4 riders, they're drafting, and it's the overall performance of the entire system that you think will be better with this new position for Rio.
Exactly. Right? Yeah, that's exactly right. And what's really key about this sport, or this discipline, is it's one thing how fast you can ride on the front. It's another how much recovery and how much rest you can get while you're not on the front, because the amount of drag that you have on the front is exponential. I think it's 30 to 40% less when you're riding behind your teammate. So the rest and the recovery is paramount. So all these changes and this change in understanding, the change in the rules, led us to need some different hardware. We actually needed, we couldn't have this one-piece bar. It didn't make sense anymore. It was just far too expensive, too bespoke, and the rules changed also. We couldn't have totally bespoke products anymore. So we had to make a major change, and we had to actually produce a new handlebar, which I'll show you on the next slide. And then the final position on the right is our Tokyo position. And this is a massive departure from everything we had done in the past. You can see the hands are touching in the center. The rider is much higher up. I don't have a great side view to show you, but her torso is much higher. And the head is nearly tucked behind the hands. So before we were low and wide, now we're high and tight. And the drag reduction of this was astronomical. It was night and day. And the reason that we needed this, the rules didn't change significantly. It was more that the power required on the front to go the speed we needed to go was impossible with the old positions. So the old positions allowed for a lot of recovery, a lot of control, a lot of visibility, but they just weren't fast enough. So we had to sacrifice those things, that control and that visibility, for just the aerodynamics that we needed. And you'll see why later with the formula and the explanation of drag in cycling.
And unlike Formula One, unfortunately, you don't have a drag reduction system where you could be low drag if you're at the front, and you could recover better if you were behind. But yeah, okay, fascinating. Thanks.
That's funny that you mentioned that. So we actually sort of do have a DRS system that we have built into these positions. So if you look very closely, Annie is here on the right. She's being held up. We have devised into this position or this setup two viewpoints for Annie. So when they are riding on the front, they need to see the track in front of them. They need to be able to steer. They need to be able to ride smoothly. So when they're on the front, Annie will actually lift her head slightly and look over her thumbs at the track ahead of her. She can't see directly in front of the wheel because her thumbs are in the way, but she can see far enough up the track to steer. So she lifts her head just a bit and rides on the front. But as soon as Annie gets to the back and she starts riding in the lineup, she tucks her head even more and she looks between her hands. She looks between her wrists at the tire of the rider in front of her. So we actually have a DRS system where she just tucks her head in and looks between her hands instead of over her thumbs.
Really is like formation flying with the red arrows or the blue angels. So that how tight and the speeds people are going. It's fascinating. Keep going.
Yeah.
Keep going.
So this was, as you can see, even just looking at these pictures, it's clear to see this final position for Tokyo is such a drastic change from the previous two iterations. So to give you a better idea of how different that bar is and how different the positions are, on the top we have the side-on and the front-on of our Rio bar, the side-on and the front-on of our Tokyo bar and our entire Tokyo setup. So when we were developing the Rio system, the Rio setup and position, 3D printing was really in its infancy. And most of the hardware that we have or had at that time was all carbon fiber. This handlebar we needed to develop because we needed a lower position. And you can see the bar on the top right image. You can see the bar drops significantly from its mount. And that was to get the arm cups lower than the top of the frame. To do that, we needed this bar to be built. And we worked with a company in Taiwan to, they designed a CAD drawing. We then went to a 3D printer and actually had it printed in plastic, which we couldn't ride. It was just a mock-up so that I could measure and I could look at it and see if everything was going to fit properly. And then we rubber stamped it, and we had a carbon mold made for us in Taiwan. We had this bar produced as like a set piece. It was uniform, it was standard, and it was commercially available. We actually sold them to anybody who wanted to buy one. But all of it was just to get lower and lower and lower. And then on the top left image, you can see all the pieces that I had to use to put the rider in this position. You see the arm cup, which is it's a CNC plastic cup. And then we have a mounting bracket that attaches it to the extension, and then the extension mounts to another bracket, which is again CNC'd, and then that bolts into the base bar. So we had a lot of pieces. Looking at the head-on, you can see all the extra frontal area it's created to have these mounting brackets to put everything together and create this adjustability. So without a lot of access to CFD, because it was prohibitively expensive, without a lot of access to the wind tunnel, we were doing a lot of our testing in-house with our in-house testing system. This was sort of what we came to with the technology at the time and the budget at the time and our understanding of it. On the bottom, we're seeing, again, everything we learned from this, everything we changed. And you can now see that we have these 3D additive risers that Mark has made for us. These silver pieces that you can see connecting the base bar to the extensions, that's the new riser. And from the head on, you can see the drastic curve that it takes, something that wouldn't have been possible with CNC, because each of these sets of risers is different to the rider. Each rider has a slightly different position, so each of the sets of risers will be a bit different to get them to exactly the height and the reach that they need. And then, of course, the extensions themselves are in carbon, and the tips of the extensions where they actually grab onto those are printed in plastic. So we do have some change that we can make if a rider wants a different grip shape. And in general, the positions are much, much higher. You can see the arm cups are several centimeters above the top of the frame. Whereas for Rio, looking at the top left image, you can actually see the arm cup is about 2 centimeters below the top of the frame. It was a drastic change in height. And all of this was, came about by our understanding that we just needed less drag. We just needed absolutely less drag because the speeds that we needed to go were not possible with this low, wide control position.
What speed, Dan? I don't know if you got a curve that maybe shows how important drag is, but what speed are we looking to go in the Tokyo Olympics now? And how does that compare to the Rio Olympics? Is it 1 or 2 kilometers an hour more, or?
I don't know the exact speed for you. I can equate it more easily in terms of time. So many years ago, I think it was 2014 or 15 after London, we were assisted by Canadian Tire in a very strange and interesting way. So Canadian Tire wanted to support the Canadian Olympic Committee, and they came in with analytics people. and they're like, we want to help with analytics because it's something we have a lot of access to for all of our inventory control and all of this. And the COC presented us with this possible aid. And we said, sure, this is great. We love data and we need more of it. So we got them to analyze the times, the top times from the last few years of races in the team pursuit. And they analyzed and they compiled all the data, and they figured out for us the trend in race time. So over 4 kilometers in the men's team pursuit and the women's team pursuit, the times were dropping by seconds every couple of years. So let's say in 2008, the fastest times were 4 minutes flat. And then by 2012, the fastest times were 3 minutes, 58 seconds. And
so
then
it's
by
like Formula One lap times, they keep coming down and down.
They keep coming down. Exactly. And they were able to graph this, and they plotted it, and they told us, we predict that by 2016, the medal winning time, the gold medal winning time at the Rio Olympics is going to be 4 minutes and 10 seconds for the women. And I think they said it was going to be 3 minutes and 50 seconds for the men. And this gap of 20 seconds between the men's teams and the women's teams, after they had told us this, we started to pay attention to it, and we realized, yeah, they're right. Every time we go to these races every year, these times are getting reduced by the increments that they believe. This trend continued. So by the time we got to Rio, we had an idea of how fast we would need to go. And we knew that the winning time was going to be around 4 minutes and 10 seconds for this women's team that we were focusing on. And we had been on the podium at every race we went to for years, for 6 years. We hadn't missed a podium at the World Championships, and we hadn't missed a podium at the Olympics. So we said, okay, we know how fast we have to go to win. And then we figured out how fast we could go and likely what position we would get. And we realized that the fastest we thought we could go was 4 minutes and 14 seconds, which would get us on the podium, but just barely. And that ended up being the case. And we finished third with 4:14.7, I think. But that trend continues. From the analytics that Canadian Tire did, that trend continues. And we know that just getting on the podium, we're going to have to go under 4 minutes and 10 seconds because the speeds are just increasing and increasing. The times are coming down and down and down. So
let's just so that we kind of stay on track here, because I'm sure there are going to be some questions from the audience. Maybe if you could just sort of wrap it up for us in a minute, and then we'll have a look at how these parts got made.
Sure. So this final slide here is the best example that we have of that. So knowing how fast we need to go tells us how much power we need to do, because this formula, the formula is not here, but the graph shows the formula that we base our decisions off of. The rolling resistance, which is tires and bearings, is pretty stagnant. It's linear and it's very small. It's about 10% of total drag. The drivetrain, which is the cogs and the sprockets and the chain, it's 5%. But 85% of the drag on the bike is aerodynamic, and it's exponential as well. So as we need to go faster, we need to produce even more power. And this is why the aerodynamics, and this is why all these positions and the changes and the 3D printed risers that reduce our frontal area, all of this always comes back to this graph or this understanding that 85% of drag is aerodynamic.
Fantastic. Thanks. Absolutely fascinating. So let's give Dan a break here right now, and maybe we can have a look at how these risers were designed and manufactured. And this has all happened just over the past few weeks, so this is very much live data. So Megan, if you could play the process video explaining how this got done. Thanks.
The first step was to capture the handlebar configuration for each athlete. Millions of data points were collected using a robotic system and structured light fringes. A CAD model of the existing structure was then constructed from these data points. An improved structure could then be designed, customized for each athlete's unique riding position. The new design reduced drag by over 20%, reduced the weight by 30%, and combined 7 parts into just one. With many different designs to be created, 3D printing was a good solution since it required no investment in tooling. Because the parts needed to be lightweight and strong, aluminum was the natural material choice. Laser powder bed fusion was selected as the best 3D printing solution for this combination of requirements. Like many manufacturing processes, at first sight, laser powder bed looks deceptively simple. A laser selectively melts powder spread across a platform, with the powder solidifying into the desired cross-section. However, laser interaction with powder can vary from simple conduction to much deeper penetration via keyholing. The recipe used needs to ensure energy is consistently delivered to achieve good melting and bonding without excessively vaporizing material. Too little or too much energy leads to poor density. Ironically, while aluminum is one of the easiest materials to machine, it is one of the least stable for laser melting. Computer simulation using physics-based models can be used to predict melting behavior and part distortion. Simulation allows different orientations and support strategies to be evaluated. Because molten layers need to be adequately restrained as they solidify and cool, support structures need to be added to any geometry that is not well connected to the layer underneath. These areas can be automatically or manually selected for support structure creation. Once the build is complete, these supports will need to be removed. With the build orientation determined and support structures added, toolpaths for the laser need to be generated. These toolpaths include the coordinates to be melted and the energy to be used. Different recipes will typically be used for melting the core versus melting the outer profiles of each layer. Powder is dispensed here from a gravity-fed hopper and spread as evenly as possible across the entire build bed. Enough powder needs to be dispensed to cover the entire bed. Due to vertical shrinkage, a little more powder is required wherever the previous layer has melted cross-sections. The process uses an inert gas, usually argon, to prevent oxidation of the molten material and to blow spatter away from the bed. Here, the gas flows from right to left and sparks from the process can be seen blowing to the left. Just as powder often needs to be carefully managed so as not to run out, good gas flow is also critical to ensure a clean path for the laser beam without blowing powder off to the bed itself. At the completion of the print, the build platform is at its lowest, with the parts fully immersed in the powder bed. Personal protective equipment is necessary to prevent inhalation of powder wherever the chamber door is open. Powder is progressively removed around the parts and then sieved to remove any oversized particles that have sintered together. Powder can then be reused. The parts are welded to the build platform, which is unbolted from the machine. Parts can be separated from the build platform using a saw or wire ADM as shown here. Printed components nearly always require finish machining to create accurate, smooth interfaces. Planning how the parts will be held for machining and leaving sufficient stock for cleanup is a critical part of the manufacturing process. In this case, 2 bolt holes were printed to allow all parts to undergo a common machining operation for the handlebar interface. Machining consists of drilling and threading the 2 bosses and leaving the part carefully tapped to the mounting bolts. After machining, inserts are fitted into the opposite end where coarse screw threads were printed to take the inserts. Finally, the aerodynamic surfaces are carefully polished by hand. Inspection of the completed component is performed using non-contact structured light fringes. We hope that additive manufacturing will help Canadian cyclists win Olympic gold in Tokyo.
Brilliant. Okay. So ambitiously, we're trying to do two stories in the hour. So I'm going to move straight on now and welcome Ben. Thank you for joining us, Ben. So before we get into looking at what Gibli has just produced, the G10, could you just give us a little bit about your background in cycling? Give us a little bit of context, if you don't mind. Thanks.
Sure. Thanks, Mark. And thanks also. We appreciate the opportunity to be part of this webinar and to share our story. And it's an exciting milestone for us too, to go from the secretive conversations we had last year to actually moving on to pre-sales and being able to talk about it here. So the foundations of Gibli really started from personal experiences and wanting to solve a problem for us. So when I met Mark Ernsting, my co-founder, about 5 years ago, at the time I was working on building a wind tunnel force balance with the University of Alberta. And really bikes have been central to my entire life. And I competed in my first race at the age of 8 and just kind of will and always have been, which is really a part of really the passion that we have for this. And then Mark, kind of the other side of this, really puts my competitive cycling days to shame with 5 national championships and being named one of the most influential people in the sport in Canada. So really combined both our backgrounds in the sport has really added to our excitement for Gibli and this product, as well as the partnership with Cycling Canada and to be able to have the opportunity to help our own home federation.
Okay, fantastic. So, some serious credentials that we've got here today. So my riding my bike down to the south of France when I was a kid, nothing. So let's have it. I'm going to make it a world premiere. Megan, could you play us the Gibli video so that we can have a look exactly what's been developed? Thanks. Awesome. It's super impressive, and really delighted to be sort of featuring a startup story here, a high technology startup. So presumably it would be fair to say, Ben, that Gibli isn't developing this device just for the 20 athletes who are going to the Olympics. Give us a little bit about what you see as the who's going to benefit from this device.
Yeah, exactly. So obviously this conversation is focused around that high-level elite athletes, which are obviously they are, and other teams are extremely interested in this technology. But really, we also see this being extremely beneficial for the kind of weekend warrior type athletes around the globe. So as an example, there's around, if you look at registered cyclists and triathletes globally, there's around 9 million triathletes and around 5 million cyclists registered in a racing organization that's kind of on a more amateur level. So all those individuals, it is extremely expensive, as we kind of alluded to with Dan earlier, to access a wind tunnel, and often not very practical because they're only located in specific geographic locations. So having access to this on a global level as a consumer product, we think will make a massive difference just from having that access to being able to set yourself up and then also being able to see it in real time.
So this device is going to let athletes improve their performance by measuring their drag in real time. Is that right? In combination with a power meter. So it's a combination of hardware and software that presumably you didn't just dream up in quite as fast and slickly as the video makes it sound. It's presumably been in development for quite a long time to get both the hardware and software to work. I mean, the pitot tube alone looks highly unusual to me. It doesn't look like, I'm a pilot, it doesn't look like a pitot tube you find on an airplane. Can you talk a little bit about that?
Yeah, sure. So I guess there's a few parts to that. In terms of development, it definitely didn't come together that quick as it looks like in the video. We've been working on this for about 5 years now, but we've kind of had independently, Mark and myself have thought about this for many years before that, and I have notes from a notebook from probably 5-6 years before that even. So it's been a very long time in terms of development time, and it really comes down to having extremely highly accurate and well built and tuned for the application hardware, because it is an extremely noisy environment that we're dealing with. So that is really absolutely critical. That has taken a long time to really nail down. And then also the software aspect of it, because you're still getting the noisy data. Now we can capture it accurately. How do you translate that into what we're doing is basically being able to detect the difference between gloves and no gloves, which is a very small change on a CDA level that we're extracting from a very noisy road environment. So sorry, go ahead.
So, that was going to be my question, so does it actually work? Can you give us an example? What could somebody expect to see if they use this device? How do you get better with it?
Yeah, so we see it as kind of for everyone. If it's a team like Cycling Canada, or it's a regular kind of weekend warrior athlete that does one triathlon per year, we see it as kind of having similar type benefits that they can get. One is being able to set up your position, first of all. So which helmet works best, which position works best, kind of a similar experience that you would get in a wind tunnel, and optimizing your equipment and your position. The second use case, which we think is also a complete game changer to the sport, is being able to see that number in real time. So be seeing your drag coefficient change live as conditions change, as you get fatigued and your head angle changes, your elbow angle changes, you sit up a little bit more without even noticing. And we're seeing on the setup side, athletes that we've tested on a kind of more amateur basis, we're seeing 15 to 20% improvements by just a couple hours with the sensor, which is absolutely massive in terms of thinking of gaining that much power from training, which would take
it is anybody
on your level years.
Done anything 15 or 20%. Sometimes you can spend years trying to get 1 or 2%, can't you? So that's amazing that you think it can have that kind of an impact.
And then one just quick example of an individual that we tested too. So this is some testing we did in Edmonton, Alberta. And it was an individual that's raced for quite a number of years. He had what he thought was a very optimized aerodynamic position for his time trial. When he came in, we did a bunch of different testing with him over 2 hours. In the end, we recommended he buys a new helmet, which we found was faster for him. We, similar to what Dan was talking about, modified his elbow positions for him, actually, because he's a tall rider. We widened his elbow pads slightly, and we removed his shoe covers, which it's kind of different for every situation. This will not work for every athlete, but in his situation, it was actually faster without shoe covers. And from those, we measured that was about a 12% drag reduction, which his target event for him was a 40K provincial time trial championships, and we calculated that would save him around 2 minutes and 15 seconds based on that savings. And a couple of weeks later, obviously not a whole lot of training would have changed, but with those equipment changes, he actually won the provincial time trial championships and was super excited because he was beating people that he'd never beaten before. So it's a really cool story, and there's a couple of those stories that we've got.
There's hope for all of us. Fantastic. And interestingly, throughout this, Dan talked earlier on about how you'd 3D printed the handlebars prototyping, and again, we 3D printed the risers in plastic just to make sure that we'd maybe got something that was sensible. Ben, have you, has Gibli used 3D printing in your journey? Can you talk a little bit about that?
3D printing has been absolutely instrumental for us. Since the very beginning, we've used 3D printing. Up until last year, we've outsourced everything. The shutdowns and everything, and kind of a scale at which we were growing at and moving, speed we were moving at, made us decide to actually bring that resource in-house. And so we print everything from our actual manufactured part in the end. And will be is 3D printed, and all the way down to test jigs and mounts and kind of a wide variety of things that has been really instrumental in my mind in terms of design flexibility, design speed, because we can do CFD work in the morning on a design, make a design change from those findings, put it on the printer and have it on a bike testing that same day, which the speed that we can develop doing that is absolutely necessary for us to do what we're doing.
And if you don't mind me asking, because I think this would probably be interesting for the audience, so you outsourced originally, which makes complete sense for getting parts, and then you decided, for a variety of reasons, you say development speed, the pandemic, you were going to bring this in-house. How did you go about selecting a printer? Can you just talk to that? Because that's a key question. How do I've always sent it to a bureau maybe. Now, how do I choose my own one? How did you go about that?
Yeah, so I've had quite a bit of additive manufacturing experience before Gibli as well, so I kind of had a good sense of the different technologies and materials out there. During the whole process of creating this sensor before bringing it in-house, we tried a whole bunch of different materials, different processes, and we have one key constraint that we have internal cavities, which are extremely small and extremely intricate, and there's only a very small number of technologies in the world that can actually produce that. So that's kind of limited down to 2 initially. Our first printer that we bought was kind of a more entry-level, more prototyping machine that we bought we'd outsourced parts on before. And then we actually recently bought a more industrial quality printer, which we'd also been working with through a print bureau for probably the last 4 years using the exact same printer, because we kind of nailed it down as in terms of material properties and the print technology to be able to produce the parts. It's really come down to basically one of the only printers and materials in the world that can do what we're doing.
It makes complete sense. That would have been the process I would have followed. And there's small intricate channels. Are those, you have 2 little ports on the side that say and you have differential pressure sensors. Presumably that's part of the intricacy inside the part. Is it the need to have pressure delivery to these devices?
Correct. There's that, and there's also some cool features that we'll be kind of releasing in a video fairly shortly too, and that's the extra feature that we have. We'll do a quick demo here. We have a removable tube, and by separating these 2 parts, it's done a couple things for us. One, if you crash, I'm just showing kind of a clear one. This is the manufacturer version. If you crash, you can replace them. If you ride in bad weather conditions, which we think is absolutely crucial for this to be able to kind of be on a bike as just a power meter or any other type of hardware that you have on your bike, you can clean it afterwards. That was one of the really challenging design solutions or problems that we've worked on the last year. And so basically when you remove this tube, we have what we call a tube cleaning device, which you screw into the bottom of the case. And then it has extra cavities which internally protect your pressure sensors so you don't blow them out when you're cleaning it, but allows you to clean it. So there's some very complex geometry inside that allows that to happen.
The devil is always in the detail. Yeah. And as you say, it's one thing to design something to work in maybe a laboratory or wind tunnel environment. It's another thing, for the, as you say, a weekend warrior who just wants to bolt it on and make sure that it works. Fantastic. Let me just because we're gonna finish. We're gonna play the show reel again at the end for anybody who missed it at the beginning, which kind of will retell the story in 90 seconds. Ben, can I just ask you, Gibli now, how big is it as a company, and where do you hope to be in maybe a couple of years' time in terms of growth?
Yeah, so we're growing very quickly. We just moved into new office space, kind of building out our manufacturing capabilities here. We're currently about 6 full-time employees. We're working with a number of consultants full-time. We've got several partners that we're working with globally. A number of
here is where again, in the beautiful Maritimes of Canada, is it not?
Yeah, so we're actually split. So our head office is in Halifax, Nova Scotia. So it's kind of where most of our resources are based. Mark, my co-founder, and a couple other staff are actually out west as well in Vancouver. So we kind of span the province or span the country. So our goal in a couple of years really is kind of laying that out. Our pre-sales opened early this month. Our plan is to deliver parts by June for our pre-sale and hit the market. And then we are kind of in conjunction with work that we're doing with teams like Cyclists Canada. We're really making sure that we stay on the cutting edge of this technology, and we have a lot of extra features that are coming down the line, which will take basically all of our attention because we're fully focused on aerodynamics and staying world leaders in this technology. And there's a lot of really cool features down the road for the next couple of years that Gibli will be very focused on, including some software additions that we think will be big game changers too.
So it's going to be just like Tesla, is it? We'll get a software update and we'll have a new device. So fantastic. Listen, guys, it's been great having you both here. It's been pretty packed. Dan, sorry, I rushed you a little bit. Clearly, we could have spent an entire hour talking about how to go faster, but I'm sure all of us in the audience wish you and the whole team the best of success in Tokyo, and we'll be alchemists if we can turn aluminium into gold, but really hoping that we can do that. And Ben, wish you all the success for the future, and again, a great Canadian success story to have this high-tech startup. So we didn't have any, we had just one slight technical question in the audience, and I've answered that. So I think since we don't have any more, Megan, if you could play us out with the show reel. And again, thank you very much, everybody, for attending.